Let's increase it to the max assist level, 5 out of 5, and open it up. See what kind of max speed we can get. Okay, we're going about 22. Full throttle, 25, 26, 27. Come on, we gotta get that 30, 28. Hey, what's up guys? It's Dr. D-Flo, and this electric scooter has been my daily commuter to and from work for the past year and a half. I originally purchased it for about 300 bucks, but let me tell you, this machine has actually saved me a lot of money because I don't have to pay for gas or a parking pass. However, hundreds of miles to and from my house have really taken a toll on the battery life, and instead of buying a new battery or even a new scooter, I've decided to go the DIY route. Now, I'm not going this route to save money because, let's face it, it would be really hard to make something of that quality for less than 300 bucks in my garage. But instead, I want a reason to use all my newly minted CNC machines that I've built over the past year and published on this YouTube channel. Also, it seems like all commercial scooters look the same, so this is a great opportunity to build something unique. Now, there's two design criteria for this build. The first is that the scooter has to be reliable. I can't be late for a meeting because my front wheel flew off. The second criteria relates to speed. Now, it kills me when I'm going up a hill and I have to use some manual power. Now, this is a first world problem, but it really hurts the ego when I'm passed by the fast jogger or the cyclist. So for this build, the scooter needs to be able to go uphill at a reputable speed. I'm not sure what that is yet. Let's go ahead and meet back in the garage to discuss the plan of action. Before we talk about design plans, I'm going to quickly go over the anatomy of a scooter so that everyone is on the same page. You have a front wheel that is connected to the steering column with handlebars at the far end. The steering column is connected to the deck of the scooter through a component that is known as the headset. The headset contains bearings which allows the steering column to rotate independently from the deck. This is effectively what allows the rider to steer the scooter. Now, of course, an e-scooter has a motor. Let's meet over at my bench and we'll talk about the different types of motors that are possible with an e-scooter. There are two different types of motors commonly used in e-scooters. The first type is an external motor that sits on the deck of the scooter and drives a back wheel by a chain. The second type of motor is one in which the motor is actually integrated into the wheel itself. This is known as an in-hub motor. With this design, you don't need a chain or a sprocket, it's a direct drive system. As I said in the beginning of this video, I'm not going to put an emphasis on saving money, so I went with an in-hub motor and a powerful one while I was at it. This bad boy is rated for 1,000 watts of power consumption, which is pretty ludicrous. It's wider than my other scooter's tire, which should allow for better traction when accelerating and deaccelerating. Now, I could use an in-hub motor in both the back and front tires, but 2,000 watts would require a mini nuclear reactor for power, and I honestly couldn't control that much torque. This is going to be a daily driver, not a speed racer, so only one wheel will be under power. I'm thinking of putting the motor in the front wheel purely because that was the way my old scooter was set up, and I would like the scooters to handle as closely the same as possible. To get this project started, I wanted to make sure that this motor actually works. This is an imported product after all, so I'm going to machine the forks that are going to hold either side of the axle, as well as the part that connects the forks together. This will allow me to hold the motor in my vise. The forks and pretty much every other part will be machined out of aluminum. This is going to be a pretty beefy design, so I'm a little worried about weight, but we will cross that bridge when we get there. I'm still debating how much talking I'm going to do during this build. Part of me wanted to just put together a montage of the entire build and send it to some nice electronic music, but there's going to be a lot of teachable moments during this build, so I will share those with you as they come up. Just keep in mind that I'm not an expert in scooter building or machining for that matter. I'm just a guy building stuff in his garage. Let's talk about raw material. I purchased aluminum in an assortment of sizes from Midwest Steel and Aluminum Supply. My rough CAD design of the scooter helped me pick some of this stock so that it was close to the final size as possible. For the fork, I'm going to use this 1/2 inch or 12.7 millimeter thick flat bar. Let's scoot over to the mill. The mill is relatively unchanged since my conversion video, but there are two significant differences. The first is that I am using Tormach's TTS tool holding system. So with this system, I no longer have to touch off my tools every time I put my tool in the collet because the tool holder mates with this precision ground surface so that when I insert a new tool, it'll be the same height that it was when I first touched off that tool. This is going to expedite how quickly I can start ops, and when I have a part that requires a couple different tools, it's really easy to switch between them. The second change is that my first electronic probe that I had, stopped working a couple weeks after I published the video. It was no longer triggering when it bumped edges. I'm thinking it's premature electrode wear, but I'm not quite sure. Nevertheless, I have a new probe of much higher quality. It's the Hallmark ITTP probe. It works with the Tormach TTS tool system. And once I dialed in the concentricity with these set screws, I was able to get about 1/2 thou of run out, probably even better. I just couldn't measure it with my indicator. The mill is still running Linux CNC with the probe basic GUI. This allows the probe to quickly and efficiently find the corner of the work. Just get it in the rough spot. Click the left corner button. And we're off to the races. I'm still working out what feeds and speeds this benchtop mill can handle. I do have to run the mill pretty conservatively because these light benchtop mills lack rigidity. I use carbide end mills, and if the mill pushes these cutters through the material at too high of speeds, they will start to vibrate, which is known as chattering in the machining business. This chattering will eventually lead to tool breakage. For those wondering, on almost all of my cutting operations, the feed per tooth is 4 thou, or about 100 microns. So I made a second identical copy. There's 2 sides to the fork. Now each one of these sides has a flat that matches up with the flat on the axle. And this prevents the axle from just spinning in this hole, because if that were to occur, you wouldn't go anywhere. The 2 forks will connect to a centerpiece that will sit above the wheel and will eventually connect to the steering rod. When I was first designing this scooter, I wanted to have as few parts as possible because I thought this would look better aesthetically. For example, this part will connect to both the forks and the steering rod instead of having two parts, one for each purpose, and bolting them together. However, with this approach, I had to purchase long end mills. There are two problems with this. The first is that these tools are expensive, and the second problem relates back to rigidity. The long stick out of the tool makes them more likely to chatter, and again, the mill isn't very rigid, so this is a compounding problem. You will notice that whenever I use this long tool, the sidewall of the part looks kind of speckled, dull in some places and shiny in others. This is because the tool is vibrating into the wall and gouging it instead of slicing right through it. To illustrate my point, this part was cut with this longer end mill, and this part was cut with this shorter end mill. You can definitely tell the difference in the finish of the sidewall. Okay, so now we can add that centerpiece. It just bolts into place on either side of the fork. With the fork assembled, I can throw the wheel in my vise. This will allow me to make sure that it works appropriately. I would hate to get too far down the line and not have the motor or the controller work properly because they're kind of paired with each other. The in-hub motor wheel came with a 1000 watt motor controller, a small display, throttle, and brakes. These controllers are notorious for coming without instructions. Fortunately, it looks like all of these electrical components come with a unique connector, so it shouldn't take much guesswork to figure out what plugs into where. The motor has a handful of wires coming out of it. These 3 wires are what power the copper windings. Now, I'm not going to go into the details of how this 3-phase brushless motor works because I would need to take the motor apart to explain it properly, and if I did that, who knows if I'd be able to put it back together in a way that seals out dirt and water. But here's the takeaway. To keep this type of motor spinning, the controller needs to know the position of the rotor so it can figure out which phase to power, so that the rotor is pulled in the correct direction. There are Hall sensors which detect changes in magnetic fields positioned along the perimeter of the motor. Output from these sensors help the controller keep track of the rotor. The wires for these Hall sensors are right here. I will drop links in the description to some great resources that explain the anatomy of this type of motor and how it's controlled. I will match these motor wires up with the corresponding connections and colors on the controller. That takes care of the phase wires. So I don't actually have a plastic housing for these Hall sensor wires, so I'm just going to plug them in individually. I'm now going to plug everything else in, starting with the display, then the throttle, and finally the brake levers. Now you may be wondering, why do these brake levers have an electrical connection? Because usually they just pull a brake cable, and that's what causes the force to be applied on the caliper. Well, there's actually a button hidden in here, it's kind of hard to see, that when the lever is pulled, it actually sends a signal to the controller to cut power to the motor. This way, if you're braking and you accidentally hit the throttle, the scooter is not going to lurch forward unexpectedly. Now there are other wires here with additional functionality, but we're not going to worry about those right now. These controllers are compatible with with different wheels and different systems. So really, I'm just going to use what I need and forget about everything else. This is a 48 volt controller. I went with a 48 volt versus the more common 24 volt systems because you can get more power with less current in a higher voltage system. For example, this motor is advertised to draw 1000 watts. Whether this is true or not will remain to be seen, but for example purposes, let's just assume the manufacturer knows what they're talking about. Drawing 1000 watts at 48 volts would mean nearly 21 amps of current. Drawing 1000 watts at 24 volts will be double that current at 42 amps. Higher amperage means you need thicker wires, so usually it is better to go with higher voltages so you can minimize wire gauge because smaller wires are easier to manage and to make connections to. For now, I'm going to use a 48 volt power supply to provide power to the controller. We're going to talk about the battery a little bit later. Let me just make sure positive is the positive. I do not want to mess that up. All right. We will power on the display. Whew, those are some of the worst viewing angles that I've seen. But I guess as long as the motor works, that's all I really care about. Okay, so we're on assist level 1. Woo-hoo! All right, that's pretty awesome. Let's crank it up. Assist level 2. Not bad. 3. It says 30 kilometers an hour on the little gauge. All right, I wonder how many levels there are. Assist level 4. 40 kilometers an hour. And is there assist level 5? There is. Man, I felt my bench lurch forward. It's saying 50 kilometers an hour. I will need to check the settings and make sure that matches the wheel diameter, but that was surprisingly easy. Just plug things in that match the color and the connections. Got the power supply to match the voltage of the controller, and we're off to the races. This is good news. We can keep moving on as planned. The next part we need to discuss is the headset. If we look at my old scooter, and we talked about the headset in the beginning, but just to reiterate, the headset is what allows the deck to remain stationary while the steering column can rotate. Inside the headset is a sleeve or roller bearings that allow the steering column to rotate. I purchased 2 bearings with a 1 1/8 inch inner diameter. Now the fork tube, which comes out of the fork, will slide between these 2 bearings. And the headset will act as a container for these bearings. I honestly could not decide if I wanted to go with roller or sleeve bearings. It was honestly a last-minute call, and I'm regretting it a little bit because these bearings are pretty bulky. But that's okay. It will fit with the beefy theme of this scooter. Let's go ahead and mill that headset. This mill doesn't have flood coolant or compressed air to evacuate the chips away from the cutter's toolpath. Spraying some coolant and vacuuming up the chips every once in a while seems to be sufficient in preserving tool life and cut quality on most parts. However, when a design calls for a deep hole, I have to stay close to the mill with the vacuum because those mill shavings will rattle around in the hole, hitting the tool and the sidewall, which is neither good for the surface finish nor the sharpness of the end mill. This is the tallest part that I'm going to mill. Again, there's going to be some issues with the sidewall finish because of how long I have to stick the tool out. Whenever you flip the stock to machine the backside of a part, you always want to use a feature that has been machined as a new probe point because there's a lot of variation between the edges of stock material that have been cut on a saw. I drilled a hole all the way through the part so that I could use this hole as the origin for when I flip the part. The Probe Basic software has a nice button that you can click and boom, it will find the center of the hole. These bearings seat nicely into the headset housing. You will notice that there is a slight lip on the part between the transition of what was machined on the first setup and when I flipped the part. This lip was also present on the fork centerpiece. I have a couple theories of why I can't get a seamless transition when I flip a part, but I'm going to save those theories and fixes for my next video on the mill, which will feature some major upgrades that should solve this problem. For now, I will cover up this issue by sanding each face on the belt sander. Let's do a quick dry fit of these components. First bearing, second one, fork tube, headset, no problem. The next part we need to fabricate is the compression clamp. This component will sit on top of this stack and it serves two purposes. The first is to make sure there is no axial play in the steering column and this assembly. The second purpose is to serve as an adapter piece to connect this 2-inch thin-walled aluminum tubing to this assembly. This will be what will look like the steering column. So let's go and make that in the mill. For those thinking about getting a mill for the garage, I strongly recommend building an enclosure as soon as you can. My open air design results in chips being thrown all over my garage. I spend almost as much time cleaning as I do milling. Hopefully I will be able to build that enclosure sooner rather than later. So from an adapter standpoint, this compression clamp, if I can get it in there, does a great job. But the next problem we need to tackle is how do we make sure that this fork tube is immobilized, both axially and radially. Problems with the fork tube are dangerous because I could lose the ability to steer, or even worse, lose my front wheel. My first inclination was to use set screws to keep the fork tube from moving up and down and spinning in its slot. You can see I drilled and tapped for M5 holes in both the fork centerpiece as well as the compression clamp. Now technically set screws will stop the fork tube from moving, but this is not a very robust solution. Over time as I ride the scooter, the set screws could back themselves out. A better solution is to incorporate these star nuts. You can insert a star nut into a tube, and due to these flared ridges, they can be put in to a hole, but they'll resist coming out. This is simply a way to add threading to the inside of a tube. Obviously, if you had a lathe, you could just add threading, but that's not an option that I have for today. So just to make sure that this star nut goes down straight, I purchased this little jig which sits over the top of the tube, and this rests on the centerpiece of the star nut, and then I'm going to bang on it. I'm going to grab a piece of wood and then bang on it. All right, here we go. I think I want so right now it's sitting on the top. I think we need to go a little bit farther. Now it's sunk pretty far in there. Now I'm actually going to insert a star nut into both sides of the tube. So here goes the second one. There we go. They're set about the same distance then, which is nice. There's actually a hole in the bottom of here, so I got to take this thing back apart. So as you can see, there's a hole in the bottom of here, and when I put the fork tube in there, You probably won't be able to see on the camera, but that's going to line up with that threading on the star nut. I got this cool titanium bolt. I bought this from a bicycle set. So obviously with enough force, you could rip that star nut out. We just want it to be tight enough that there's going to be no play in the fork tube. So the star nut is going to resist, axial motion. It will still allow for the tube to spin, which is not ideal, but we're going to use those set screws I talked about before to prevent that radial motion. So a feature that I want to point out that I haven't before is that both the centerpiece for the fork and the compression clamp both have these ridges on them, right around the outer diameter of the fork tube. And what those are for is that they will mate with the inner don't pound on your bearings. They will mate with the inner raceway of the bearing so that even when this thing is compressed, it'll still spin. It's not going to have to overcome friction on that moving face. Go ahead and put the headset on. That star nut slightly deformed the top of the bearing. If you look down the barrel of the compression clamp, the only way to prevent that bolt from falling into the star nut is going to be to have a little plate. So we got that, and this will sit right in there. So we'll put the compression clamp on top. We will use another bolt. And so there I just stuck that bolt in there and it threaded into the star nut. And you can see here, this guy still spins, no problem. What I want to check though is if I put this 2-inch steering tube in here, it's going to act as a fulcrum. We can check and see if there's any play. Now there's no set screws installed yet, but you can see it's very rigid. You don't want this to be loosey-goosey when you're riding. One of my only concerns with this setup is that the compression is actually going to place an axial load on those bearings, which they're not meant to be under axial load. I'm curious if I should have used angular contact bearings for this setup. Let me know in the comment section below if I should make that change. I don't think that there's anything dangerous with using these bearings. If they fail, it'll just be hard to steer. That's about it. So I'm going to push ahead. That fork tube can still kind of rotate in the housing. These set screws are going to prevent that. I don't want to over tighten these set screws because they can deform the aluminum tube, and then it would be almost impossible to get the bearings off if both ends are malformed. So just nice finger tightness. I want to point out that I will have all the files and parts required to build this scooter on my website. For the very few people who do follow along with this build, please note that you're doing it at your own risk. I'm honestly not sure how safe this will be, so I'm trying to err on the side of over-engineering each component. I'm counting on the comments below to help me revise this design for future iterations. Now, something I want to point out to you on my old scooter is that the battery was stored in the steering column. However, commercially available batteries, especially those that are 48 volts, do not come in this cylindrical form factor, or at least I couldn't find it. So I'm going to put the battery in the deck. So why did I go with such a big tube? Well, for one, again, it's going to fit this overall beefy design that I'm going for. And two, I got my start on YouTube by being the LED guy. My LED videos started getting a lot of views before any of my other content did. So what I want to do is pay homage to some of those beginning videos by inserting a long light bar along the distance of the 2-inch tube. So I cut a 1/2 inch strip down about 3/4 of the tube with the mill. I didn't want to go all the way to the end because I didn't want to compromise the mechanical integrity of the tube. And then I actually took a light diffuser off of one of my ceiling LED lights and stuck it in that slot. And I think it turned out pretty good. All right, so I went ahead and hooked up a strand of double row LEDs, add a little bit of extra brightness, to a 12-volt power supply. So yes, the LEDs and some other things I'm going to put on the scooter are going to have to operate at a lower voltage than the motor, but we'll cross that bridge when we get there. Let's see what this guy looks like when it's lit up. Not bad. I mean, it's going to look even better when I'm riding at night. With this light bar and the sharp lines of the scooter, I think I'm going to dub this build the Cyber Scooter. Yeah, it's not made out of stainless steel like Elon Musk's truck, but it's going to look sleek. It's going to look like it's out of this world. It's going to look like I'm rambling, and I am. So that's seated nicely. We're going to come back and do the LEDs when we do all the electronics. But next up, to finish off this, steering column, we need a way to steer. So we're going to add the handlebars on this piece of aluminum tubing, but we need a component that acts as kind of like a T-joint where we can connect the 2-inch and this smaller tubing together. So the left brake, throttle, and right brake all slide onto the handlebar, and I'll screw them down. The display used to have one of these loops, but I since removed it because that's just a lot of stuff hanging off the handlebar. What I wanted to do was inset the display into that T, that piece that will connect the handlebars and the 2-inch steering column at a right angle. So when I was looking to inset this, I need to know this outside geometry. It's actually kind of a weird shape. So instead of just kind of guessing and checking and running right over to the mill, I actually started to 3D print a series of templates until I was able to closely match, these weird contours around the edge. You can see here that I found the geometry both on the front and for the mounting holes on the back. And so from here, I was able to then go with my digital design straight to the mill, and I knew it was going to come out great. For those who are looking to get into hobbyist machining, I should warn you that tooling is a significant hidden cost. Between all my end mills, drills, chamfer bits, taps, and a sizable number of Tormach TTS holders, my milling supplies almost cost as much as the mill itself. You can purchase cheap tooling, but usually the quality control on these tools is scarce, and I found that each one cuts a little differently. This makes it difficult to figure out the optimal feeds and speeds for each operation, which is why I spend a little more when I opt to buy from MSC or McMaster Carr over Amazon or eBay. This way I know that when the mill is groaning or the surface finish is poor, it's my fault and not the new end mill's fault. This was my most complicated part that I've milled to date because I had to keep flipping it. I needed access to 5 out of the 6 sides. These are the parts where an electronic probe pays for itself in spades. So I was a little confident about this fit. Let's hope everything goes as planned. Not bad. The handlebar slides through these two holes. Once I get it evenly spaced out, it is held in place by two set screws that are found on the back. Okay, so now we can add the brakes and throttle. I have these little 3D printed spacers just to make everything look tidy. Finish this side off with one of these rubber grips. Actually kind of painful to put on. At least I know they're not coming off. Oh, that's nice. There's two spacers on the right side because we have the throttle. I wanted to keep the brakes equidistant from the center. Look at that. Tell me that's not cool. The 2-inch steering tube enters through this bottom big hole. I'm going to thread just this one wire of the display through here. I'm going to do the other wires later. Now right now, the steering tube is connected to this T-piece only by set screws. This is not a long-term solution because I would like to be able to pick up the scooter by the handlebars when I'm navigating curbs, and those set screws are just not going to be able to withstand those forces, especially because as I tighten the set screws down, they will deform the thin walls of this aluminum tube. This setup will be fine now for testing purposes, but I have a couple different ideas for how to make this connection stronger, and that'll be coming with future iterations. And that finishes up this steering column front wheel assembly. Time to start working on the deck. This scooter will house the battery and electronics within the deck. The deck will also have to support my weight, so it needs to be mechanically sound. My first inclination was to use the plasma cutter to make all the parts for the deck because each part would be too long to mill in one setup. However, the way I designed the deck was to have the top and bottom pieces be made out of a 1/4-inch aluminum and fasten those pieces down to the edges of the side pieces. The side pieces would be fabricated out of 1/2-inch aluminum, and they would provide the majority of the mechanical support. So top piece, side piece. One of the few limitations of plasma cutting is edge squareness. I discussed this topic in my How to Build a Plasma Cutter video, but briefly, the plasma stream that slices through the metal is shaped like an ellipse, so you're not going to get a flat edge. This is even more apparent when you cut thicker material. For this reason, I decided to mill the side pieces in two separate ops. The total length of this piece was about 29 inches or 730 millimeters. The x-axis travel of the mill is 21 inches. So the plan was to machine one side first and then rotate it 180 degrees and machine the other side. This is actually a great example of how not to set up a part. All of this unsupported material is going to resonate like a tuning fork. Clamping this part with two vices would have been the correct way to machine a part of this size. Due to monetary constraints, I'm going to have to risk it for the biscuit with a single vise. I'm not going to face this part because things can get dangerous when you have a cutter that big in a part that is not supported properly. I'm cutting hexagons into the piece to remove some of the weight. According to my CAD program, the addition of the hexagon saved a little over a pound of weight, or about 1/2 kilo per side. I programmed a small hole to be drilled because this will function as the new probe point when the part is rotated. These turned out awesome. There's a nice square edge that we can mount the top and bottom pieces to. Now, before I get to those top and bottom pieces of the deck, I finished off the sides by milling these two short plates that will connect on the inside of the long side plates. Now, this one that will sit in the front has a hole for wire management and some bolt holes that we'll use to connect the right angle brackets that will eventually join the deck to the steering column. I am going to plasma cut the top and bottom pieces, and if you've seen any of my last videos, you'll know that I love plasma cutting. It's probably the quickest technique to go from a digital design to a real life part, and fire. What else can I say? Also, if you're caught up with the Dr. D-Flo content, you will know that this Microcut 875 SC by HTP is the 4th plasma cutter that I've had on the lead plasma table. However, this is the first plasma cutter that is actually meant for CNC. It has a mechanized torch, it has 100% duty cycle, and CNC connections that give me access to more than just the trigger wires. These upcoming cuts are just going to be a teaser. I'm going to review this plasma cutter in a separate video where I will discuss how to plasma cut aluminum. So get subscribed if you're interested in that future video. For the top and bottom of the deck, I'm not going to do anything fancy, just a rectangle with some bolt holes. I didn't want to put a design on either piece because that could jeopardize the mechanical properties of the plate. Okay, hear me out. I thought that having a bunch of bolts would continue that beefy look that I was going for, but man, did that turn to be a royal pain in the butt, trying to get those countersunk holes to line up with the tapped holes in the sides of the deck. I still can't get some of the bolt holes to line up, and it's driving my OCD crazy. So for the top design, I simplified and started with 4 bolt holes.
Where are we standing at? You're really that heavy.
Every time I go over a bump.
Alright, well, we'll revisit that tomorrow.
Now we need to connect the deck to the steering column. I made this part that has 2 faces, one for each of those brackets that will connect to the headset. This piece attaches to the front deck plate with some bolts. So now it's time to attach the steering column to the deck, and really the only requirement is that the deck is perpendicular to the steering column. Now, I thought that this bracket would be pretty easy to make because basically all we need to know is the vertical change between the headset and this bracket, as well as the horizontal clearance so that the wheel can still spin. Those constraints resulted in this bracket. I'm just going to attach it with 2 bolts because there's a flaw because I didn't consider a variable. So what happens here is, this connects fine, that all lines up, and you can see the wheel can move no problem. But the problem occurs when you steer, because the fork centerpiece and side pieces will swing out. And I'm just going to move the headset to pretend like it's turning. And you can see here that makes contact with this right angle bracket. So I went back to the drawing board and I came up with this design. Basically, I use these hexagons to kind of disguise my mistake, and these cutouts will actually be where the fork's at. Let me show you. So this is quite satisfying. You can see it just manages to clear. I mean, you could do a 360 if we didn't have all the cables. It works for the other side as well. There was a small amount of play at the base of the steering column, and this little bit of movement translated to a lot of movement in the handlebars. Now, I don't want to be going forward and back every time I accelerate and brake, so I want to fix this now. I ended up with 3 modifications, which I think are going to solve the problem. The first is that I milled this compression clamp to have a tighter fit with the 2-inch tubing. It's no longer a slip fit, but is instead an interference fit, which means I need to bang that tubing on. This should fix a lot of the problems. The second change I made relates to the 2-inch tubing. Now, one thing I noticed was that when I was tightening those set screws in, they never seemed to get tight. And when I pulled the tube out under further investigation, they were actually denting the tube. So I went with a thicker tube. This new tube is about twice as thick, and it just feels a lot sturdier. The third modification are these 2 pieces that I created, and I'm calling them the securing clamps. They have 2 functions. The first is to prevent the tube from rotating, and this is accomplished through this bolt that runs to either side of the clamp. Finally, they're positioned on the tube in such a way that there's going to be a small gap between the bottom face of the clamp and the top face of the compression clamp, so that when this thing is fully seated, again, it's going to have to be banged into place. There'll be a small gap, and I can use screws to further force this tube to be fully seated in its housing. This should prevent rotation and upward and downward movement. Now, this clamp is on both sides, so it's going to work for both the compression clamp as well as that T-joint piece. Before we attach the steering column again, I want to go ahead and run all of the wires. I took the throttle, brakes, and display wires and put them in this cable just to keep them all tidy. I'm going to do the same thing for the LEDs after connecting them to this button. And the button is housed right in the back of the steering column. Put these wires and put the steering column or handlebar wires in first, so that we can get the LED to hopefully LED strip to rest on top of them. Okay. The most important component. I don't know if the scooter would work without the LED strip.
Why not?
Okay. Let's get long bolts now. Come at me, no play. Ah, yes. Perfect.
Is that enough?
Yes. So this is looking pretty lined up. I think we're gonna, so much sturdier. It's gonna be a lot heavier, but definitely sturdier. I reattached the steering column and the deck off screen, so now it's time to talk batteries. The last thing I wanted to do is buy an undersized battery that could only power the scooter for a couple of miles. I would be better off with my old scooter if this was the case. So I bought the biggest battery that would arrive in a reasonable amount of time, and I ended up with this behemoth, 20 amp hour at 48 volts. It is more likely that you'd find a battery like this on an e-bike, but when you build your own scooter, you can do whatever you want. I looked at some distance calculators online, and this battery should propel me for over 50 miles. This is totally overkill because I could travel to and from work 10 times before having to charge, but now distance will never be a limitation, and if I forget to charge the scooter after I get home, it won't be a problem. Okay, so we can now drop the battery in. You cannot ask for a better fit. In theory, this whole deck should act like one large heat sink and suck the heat away from this battery, but I'm going to monitor this temperature as I ride for longer durations. Next, we need to connect all the wiring to the motor controller box. And I went ahead and drilled and tapped some holes at the bottom of the base, so this will bolt down at these tabs. It's getting evident that I'm going to need a kickstand. Now for the LED light bar, and these two little lights that I've included on either side of the deck, which will provide kind of a cool underglow at night, will be powered by 12 volts. So to step down the 48 volts of the battery, I'm going to use this little 48 volt to 12 volt converter. Now it's pretty bulky because it can handle a lot of current. Obviously these LEDs aren't going to draw anything near to what this thing is rated for, but this should be more efficient than just using resistors. So the positive lead will go up to the button. It's a latching button, so when the button's clicked, it'll connect the circuit for the LED as well as these two lights. I created these little wire harnesses that will allow all the LEDs to be connected. There's an open spot here in the wire harness because I have some plans to put some rear lights on, maybe a turn signal, not sure yet. This converter is just going to sit here on the side. It's just going to kind of rattle around in there for now. And I created a main power harness, which will connect to the battery, to the 12 volt converter, and to the motor controller. Now when I plug it in, there will be a little bit of arcing, which you think I would be used to it by now, but it scares me every time. So if I flinch, you know why. Okay, so this is red. Just double checking the wires. I think we're good. Here we go. I don't know where it has to arc. Gosh, like I said, it scares me every time. Hold on one second. Okay.
The LEDs worked.
Yay! Lastly, we have the charging port, and I'm actually happy with how I was able to disguise the mounting hole with the other hexagons. This will just plug into the battery as well. We can put the deck plate on. Andy actually applied some non-slip tape, which will keep me from sliding around on this plate. The last major thing that we need to tackle is the braking. Now, if you remember from early on in the video, the brake levers have electrical connections that tell the motor controller to stop and slow down that front wheel when they're pulled. This is known as electrical braking. Now, if the battery doesn't have power, then you can't brake. So I want to include a mechanical brake on that back tire. Now, it wasn't trivial to get that red caliper to line up with the rotor, because if it was too high, it would rub on the tire, and if it was too low, it would rub on the rotor. So we're just going to connect that mechanical brake line to one of these brake levers. It'll look a little weird, one not having a wire coming out of it, but that'll just be used for the electric braking. Just using these little 3D printed pieces to cable manage this tubing that the brake line will run down. Now with the brake line, you don't want any tight bends or else it's not going to work properly. So I'm trying to leave extra room around corners and of course at the bottom of the steering column where it's going to have to rotate. We're going to run the wire along the bottom of the scooter to the brake caliper. There's steel cabling in there.
Should I go all the, hold on, let me go all the way in.
Yes, this is kind of cool. Okay. I don't know if that will hit the wheel. That'll be interesting. Do you want to give this guy a pull? We did it!
Sweet.
That's awesome. But before we take the scooter out for a spin, I want to point out this is my first iteration and there will be a follow-up to this video. There are still some features that I want to add, like making the scooter foldable so that I can throw it in the trunk of a car. Also, these are solid rubber tires. They're not pneumatic like my old scooter. So I'm wondering if there's going to be a lot of vibrations in the scooter and I may need to add shock absorbers. Once I'm happy with the final design, I will polish all the aluminum parts and weatherproof the scooter. I will definitely need some fenders for when it rains. Let me know in the comments below what changes or additions I should make to this design. This was a fun build and I learned so much more about how to run my mill. I could still use a lot of practice, but that's going to come with time. If you enjoyed this video and want to see more e-scooter or fabrication content, get subscribed. Follow me on Instagram at Dr. D-Flo to get daily updates on all the large and small projects that I'm working on. With that, let's get this guy on the road. Just taking it slow here in the beginning. I'm on assist level 3, going about 13 miles an hour. And man, this scooter feels sturdy. With that battery being in the deck, I've got a really low center of gravity. And with these wide tires, it feels like if I let go of the handles, which I'm not going to, it feels like I would stay upright. Steering column is still a little bit wobbly, but nothing unmanageable. I feel incredibly safe riding this right now. I'm gonna go ahead and increase it to assist level 4 and we're gonna open it up. All right, getting close, 22 miles an hour. Man, this is smooth. I was worried about not having shocks. Uh-oh. Speaking about bumps and smoothness, I was worried about not having shocks, but on asphalt, these solid rubber tires are fine. With electric motors, you have that instant torque. It's extremely responsive to pressing the throttle. Let's increase it to the max assist level, 5 out of 5, and open it up. See what kind of max speed we can get. Okay, we're going about 22. Full throttle, 25, 26, 27. Come on, we gotta get that 30, 28. Woo! It feels so fast because my feet are so close to the ground. On flat ground, I can hold 26 like there's no tomorrow. The brakes are really responsive. I almost fell off. Just riding around downtown Nashville. Tuesday morning's about the only time the honky tonks are quiet. I mean, this is crazy. We're at 8.1 miles on this first charge, and the battery voltage hasn't dropped at all. There are 6 divisions on that battery thing, so does that mean we could go 48 miles or more? Dare I might say I bought too big of a battery? Okay, this is an incredibly steep hill. Let's see what we get. Okay, 12 miles, 13 miles per hour. Not bad, 14 miles per hour over the speed bump. 16, 17, 18.